Hello, everyone. Thanks for attending my talk. My name is Chen. I'm currently a CS PhD student at University of Illinois at Urbana-Champaign. Today, I'm going to present our paper, File System Semantics Requirements of HPC Applications. This is a collaboration project with Lawrence Livermore National Lab. So the motivation behind our project is that we're trying to understand the I/O performance of HPC applications. However, the I/O subsystem is becoming increasingly complex. As you see from the graph here, applications normally use high-level I/O libraries such as HDFI, NetCDF to perform parallel I/O, and those I/O libraries are built on top of some I/O middleware such as MPIO. And under the hood, they use POSIX I/O interface to interact with parallel file systems. There are general purpose parallel file systems like Lustre GPFS and specialized parallel file systems designed for some special hardwares like the local SSDs, which are also known as burst buffer file systems. And also there are file systems designed for non-volatile memories. So each of those components can have an impact on the I/O performance, which makes the I/O performance difficult to study. And on the other hand, most widely deployed file systems like Lustre GPFS, they support POSIX semantics. However, POSIX standard was designed decades ago for the use of a single machine with a single storage device. It is not designed for highly concurrent I/O operations like we see today. So the primary challenge arises from the strict adherence to the POSIX semantics. The POSIX semantics requires that a read operation should always return the data specified by the last write to the same data location, and a write operation shall overwrite the previous writes to the same location. So this is essentially imposing sequential consistency for reads and writes, which works fine on a single node. Even if you are using caching, as long as you keep track of the dirty pages, you should be fine. There are several ways to ensure POSIX semantics in a distributed or network system. For example, you can disable page cache and every operation goes directly to the disk, but a more commonly used way is to use some kind of locking mechanism. But both approaches can introduce performance penalties. So the real question is that, do we actually need POSIX semantics? Like many HPC researchers, we believe that the POSIX semantics is an overkill for most HPC applications. So that's why we see many new file systems developed with relaxed consistency semantics. This is based on the assumption that multiple jobs will normally not access the same file, and even within a single application, multiple processes will normally not perform operations like write after write or read after write. So we should be fine with a relaxed consistency model. However, we need experimental data to confirm those claims. Here are the key questions we are trying to answer. First of all, what are the common I/O characteristics of HPC applications? How are files accessed? Are they accessing the file sequentially or in a strided manner? Do they ever do write after write or read after write? Which metadata operations are used by those applications? Is it possible to also relax metadata operations? But more importantly, assume you are an application user and you find out a new file system with a relaxed, consistent model, but provides a very good I/O performance. Now you want to know if your application can run correctly on that file system. Now, it is challenging to determine the semantics requirements of an application because the I/O patterns depends on the execution flow of the program and also on the I/O behavior of the I/O libraries. And moreover, parallel file systems relax the POSIX semantics in different ways, and they are often poorly documented. And sometimes you have to email the developers to find that out. And there are no accepted definitions or categorizations of the relaxed semantics implemented by different parallel file systems. The goal of this paper is to provide necessary tools to help understand the I/O behaviors of HPC applications, and also to provide a way to understand the semantics requirements of HPC applications, so the users can choose the best parallel file system according to their need. And for PFS and I/O library developers, they can use such information to make better optimization decisions. And also, with such information, they will know exactly to what extent the POSIX semantics can be relaxed without breaking their targeted applications. Without such information, they have to make conservative decisions. So how do we achieve those goals? First of all, we provide a terminology for the categorization of those PFS relaxed consistency models, and we list several example parallel file systems under each category. And we also developed a method that could be used to detect I/O accesses that could potentially lead to conflicts under weaker consistency models. And finally, we collected I/O traces from 17 HPC applications, and we present our study on the I/O characteristics of using those traces, and we have made all the codes and dataset publicly available. So now we show our categorization of PFS consistency semantics. We define 4 commonly used consistency models, and the categorization is defined according to when a write made by one process becomes visible to other processes. We will cover the first 3 here today due to time limit. The table here shows many example parallel file systems under each category. The first one we define is a strong consistency model, which is similar to the POSIX semantics. Since most HPC systems do not have a global clock, we employ the happens before order, which is defined by the program order and communication. So this strong consistency model essentially requires that a write operation should be immediately visible to the following reads. So most general purpose PFS, such as last sturdy PFS, support strong consistency model. The second one we define is commit consistency model, which is a less strict model. It requires that the writing process have to make an explicit commit operation in order to make the updates visible to others. So the commit operation depends on the parallel file system. For example, it could be a fsync operation. Many new user level file systems and burst buffer file systems belong to this category. The third one we define is session consistency semantics, also known as closed to open semantics. So in order for a write operation to become visible to others, the modified file has to be first closed by the writing process and then opened by the reading process. In other words, there has to be a close then open construct in between the write and read operation. Finally, we describe our conflict detection algorithm that could find out the potential conflicts under weak consistency models. First of all, we define an overlap to be 2 operations that access an overlapping area of the same file. And whether an overlap is also a conflict depends on the PFS semantics. So a conflict is an overlap that can potentially lead to data hazard if POSIX semantics is weakened. So here are 4 types of potential conflicts: read after write by the same process or by different processes, and write after write by the same process or by different processes. So In the majority of parallel file systems, conflicting accesses by the same process will take effect in the right order, so that only read after write by different processes or write after write by different processes are potentially problematic. Note that read after read or write after read cannot cause a conflict because we assume that conflicting operations are properly synchronized so that the read will always complete before the write starts. We represent each IO operation as a tuple of 5 files, which includes a timestamp and the process rank that performed that operation, the starting and end of that, and also the type of that operation, either a write or a read. So assume we have n IO operations. We first of all sort all those operations according to the starting offset, and then we can use a simple nested for loop to perform a pairwise check to find out all the overlapping operations. Now, this simple algorithm takes on average n log n time to finish due to the sorting phase, and in the worst case, it takes n square time to finish. As for the conflicts, the two tuples are considered a conflict pair if the following conditions are met. First of all, they have to be overlap, and the first operation has to be a write operation. And for the commit semantics, the process R1 should not execute any commit operation after T1 and before T2. And for the session semantics, there should be no close then open construct in between the two overlapping operations. We can use the same algorithm as we used for detecting overlaps to detect conflicts. But for the commit semantics, we need to extend each tuple with an extra file that keeps track of the timestamp of succeeding commit operation. And for the session semantics, we need to extend each tuple with two extra files. The first one is used to store the timestamp of the succeeding close operation, and the second one is used to store the timestamp of the preceding open operation. With those information, we are able to detect all conflicts that can lead into data hazard under a given weak consistency model. Finally, let's look at our results. We perform all the experiments on cores at Lawrence Livermore, where each compute node has 36 cores and 128 gigabytes memory. The parallel file system we use is Lustre. On the right, we show the 17 HPC applications and IO benchmarks we selected. As you can see, many of those applications support different IO libraries. So for those applications, we run them multiple times, where each time we use a different IO libraries. For all applications, we run them in two different scales, a smaller scale with only 8 nodes and 8 ranks per node, and a slightly larger scale that has 32 nodes and 32 ranks per node, for a total of 1,024 ranks. All the traces are generated using Recorder, which is a tool, a multi-level IO tracing tool that we developed. And we also have developed a Python library that could realize the Recorder traces and perform custom post-processing. So both codes are available here. And the dataset for all the traces are available in this link. And in this link, we also include the information like the configuration of each application and input files, output files, etc. So first of all, let's take a look at the access patterns of those applications. So we define 3 types of accesses. The first one is consecutive, where multiple IO operations access the file consecutively. And the second one is monotonic, where 2 IO operations access the file in a sequential manner, but there could be gaps in between them. And all the other accesses are considered random. We show the access patterns from two different views. On the left, we show the access patterns from the perspective of the parallel file system. On the right, we show the access patterns from the view of individual processes. We won't have time to go through every application. We will use Flash as an example, and the rest can be found in our paper. So let's take a look at the Flash here on the first column on the right first, which uses HDFI to perform the I/O, and the HDFI is configured to use independent MPI I/O. So when using independent I/O, every process was actually involved in the I/O phase. We plot also the actual accesses to one checkpoint file on the right here. On the x-axis, we plot the ranks. On the y-axis here, we plot the offset of that file. So you see, every process was trying to write their part of the data to the checkpoint file. So that's why when looking to one individual process, you would see a 100% monotonic access pattern. So it's actually writing the file in a strided manner. However, all those MPI ranks will send their I/O request to the parallel file system concurrently. So that's why you see on the left, almost a half of those accesses appear to be random to the parallel file system. The second column here shows the same Flash simulation, but this time we configure the HDFI to use collective I/O. So instead of every MPI rank writing to the same file, only a subset of MPI processes are selected as aggregators, and only those aggregators write to the file. So the total number of I/O requests is reduced, but each I/O request becomes larger. And since those small writes are aggregated, that's why we see many of those accesses becomes consecutive here. And we also observe a small part of random accesses pattern. That is due to the HDFI metadata operations, as we plotted in the graph here, those small red dots, which represent the HDFI metadata operations. Finally, we run our conflicts detection algorithm using session semantics. And we show the table here, the conflicts we found for those applications under the session semantics. As you can see, most conflicts occur on the same process, and which are normally handled correctly by most parallel file systems. As we mentioned earlier, the conflicting accesses normally take effect in the correct order on the same process. But there's only one exception, BurstFS, which cannot handle single process conflicts correctly. There is only one application, Flash, that shows conflicts across processes. It has a write after write conflict on different processes. So in other words, 16 out of 17 applications we tested can run correctly on a weaker model. They do not require parsing semantics. They can run correctly on the session semantics or commit semantics. And the only conflict across processes we found for Flash is due to the HDFI metadata flashes. And that could be easily fixed by only one line of code change. Other than that, we also started metadata operations used by those applications or I/O libraries or MPI. We won't go into details on this. You can find more details in our paper. We also performed more analysis and realizations using our traces. Those include function counters, how much time you spend on each function, or I/O size, histograms, etc. All of this information is available in the dataset we mentioned earlier. Finally, to conclude, so the main takeaway of this paper is that most HPC applications do not require parsing semantics. A weaker model like session semantics or commit semantics is enough for those HPC applications. This gives us the opportunity to relax parsing semantics and in order to exchange a higher I/O performance. And we hope our approach can help the community to determine the semantics requirements of HPC applications. And also we hope this information can help the PFS or I/O library developers to make better optimization decisions. For the future work, we plan to extend our conflicts detection algorithm to include metadata operations and be able to handle more complex HPC workflows that consisting of multiple applications. Okay, that's all. So thank you for listening to my talk, and I'm ready to answer your questions.